Hi guys, in continuation of the previous video, the Bohr's model of an atom, for which the energy of an electron, uh, in the orbit, that means the respective orbit is given by the expression that is En is equal to Rydberg constant divided by n square. Is a negative. The reason is because when the electron moves from the E2 level to E1 or the E outer, means if the electron, for example, here electron are there in the different shells. For example, electron moves from the here, from the either maybe to here or here or here like this. When the electron moves from the outer shell to the lower shell, it emits radiation. So because of that, it carries negative value. Because of that, the Rydberg constant value is, RH value is considered minus 2.18 into 10 to the power 18 joules. Into here he considered the generalized equation for every atom which is possessing the electron, one electron, means the any atom. For example, here atoms like the helium plus lithium 2 plus beryllium 3 plus, like this. So that means these possess the single electron around the nucleus. So for which the energy level or the energy equation considered as minus 2.18 into 10 to the power minus 18 joules into, here he considered z square upon n square, where z is atomic number and n is the shell number, orbit number. So if I consider the same for hydrogen, so here what happens, if I take the n is equal to 1 for hydrogen, for any where n is equal to E1, so then it will become for hydrogen it will become what? The atomic number is 1, so the value will become 2.18 into 10 to the power 18. But if it is 2, E2, then it will become it's a 1, the value of the hydrogen atomic number is 1, n value is 2, so the value will become, that is minus 0.5 or almost 55 into 10 to the power minus 18, that means joules. That means what? As we move from center to the outwards, the energy of an electron increases in the particular shell. So that's what the during the emission the value will become this negative. Now how to consider radius? Radius value for any generalized equation was given, that is n square into a naught, where a naught value is considered, maybe in two ways it can be considered, either 22.9 picometer or 0.53 angstrom. Both the ways it can be considered. So at that time the value of the Rn value will become 0.53 n square upon z, where z is atomic number. Z is atomic number. Next, when I apply the change in energy, I told you what? In every shell there is a change in energy. I consider this the energy of each electron in the different shells differ by del E. How to consider del E value here? That is, del E, as I said, always is the higher value minus the lower value. So here I'll incorporate, or I'll put the value of the E1. If I consider this E1, then the value will become minus of RH by, it will become N2 square minus of minus RH by N1 square. Now, if I reverse the expression, then it will become RH minus minus will become positive, RH by N1 square minus of RH by N2 square. Okay? So now I'll keep the RH value. RH is a common term, Rydberg constant, upon there is 1 by N1 square minus 1 by N2 square. Okay. So here it is for, maybe I can consider it generalized, or the E1 or energy level. Okay. Now the frequency that is considered here, the frequency, as I said, you must have known that del E by H. So the change in energy, if I put this as a change in energy, so then value will become RH by H 1 by N1 square minus 1 by N2 square. Now Rydberg constant value we know, so that is the minus 2.18 into 10 to the power minus 18 joules upon 6.626 into 10 to the power minus 34 joules second, 1 by N1 square minus 1 by N2 square. So here this is how much the frequency that is required, the wavelength. Maybe we know that the Ixpoe, if we take the visible region, it from 400 nanometer to 800 nanometer, what happens? I think we know that Ixpoe that varies here. So here the what frequency or the what radiation is required for the excitation of electron from the lower orbit to the higher. Next, during the emission, what radiation that emits out, that also can be calculated with that. Now we know that the frequency and wave number, if I consider here two ways I put. So if the bigger the wavelength, smaller the frequency, and the smaller the wavelength, the higher the frequency, and the more the wave number. You can see here the wave number is what? The more here as compared to the. So that's what we say. We know that we know the expression wavelength. I think already you must be knowing this. C is equal to frequency into lambda, where lambda is equal to C by frequency. Here if I consider 1 by wavelength, now we call that as a wave number. So that at that time it will become the frequency by C. Then what should you do here? To this value I should add minus 2.18 into 10 to the power minus 18 divided by 6.626 into 10 to the power minus 34 joule second into, here what should I do? Here the light, okay, value, C value, velocity of light, upon 1 by n1 square minus 1 by n2 square. So here the final expression that is obtained, here what I am going to get, that is wave number. It is wave number. That means the number of waves. So that expression, the value of this is 1.09 into 10 to the power the 7 upon 1 by n1 square minus n2 square. Okay. So where the wave number, to find out how much the wave that are used for shifting either from lower to higher or higher to lower during the emission or absorption of the radiation. So here we can consider, for example, if I consider n2 as n final, n1 as n initial, so the n final will be greater than ni, that means during the absorption of the radiation by the electron. That means if the nf is smaller than ni, if we consider that here, then it is observed during the emission of the radiation. So then why we have to learn the expression whole enough? That means here we know that the electron possess the dual nature. That means matter and the wave. That means dual nature. Electron possess the dual nature like particle and wave nature. So here it comprises energy as well as the wave and the, so that's what, if you look into the atom here, the nucleus, if you take the electron, consider it moves not exact with the path, it moves like the waves. So that's what, it has both the momentum as well as the wave nature particle. So that's what, how it gives you an idea. So the higher the wave number, the more brightness and the more the intensity of the emitted light, so that the light or the emission spectrum can be visualized easily, and that way. Why we have to study? The final conclusion, why we have to study? It is to be studied, application of these is, if any element, unknown element is given, so by using the emission spectrum of the element, we can find out the element is belonging to the specified molecule, maybe the particular element. So that means how? That means each element has its own characterized or unique spectrum or unique emission spectrum. How we use like fingerprint or the barcode, like that. For example, carbon has its own emission spectrum, or the hydrogen its own emission spectrum. So if unknown is given to us, so we can, if we match that one with the existed emission spectrum, we can identify. So the element which is given, that is that element. So how we can find out? By using Bohr's model of phantom. Hope you have understood. Thanks for watching.